In the previous video, we learned about the Friedel-Crafts alkylation mechanism. In this video, I want to do an example of this reaction. So let's say we're given all of this information. We have the reagents, a benzene ring that's unsubstituted, an alkyl chloride group, aluminum trichloride as a catalyst. We can recognize that as a Lewis acid catalyst. And then we're told that this forms two products here. Two different alkyl benzenes. And one is in much higher concentration than the other. So let's say now we're asked to explain with a mechanism why this is observed, why this is the result of this reaction. So we know the mechanism for the Friedel-Crafts alkylation, so let's start there. First thing we do is generate the electrophile. And one thing that you might notice is if you trace carbons from the alkyl chloride reagent to the product, for the product that's generated at 27%, the alkyl chain is bonded at carbon 1. For the product that is generated 49% yield, it's bonded at carbon 2. So there's something that's going to happen with this alkyl chloride reagent. So let's go through step 1, generating the electrophile. I'm going to actually draw out all of the carbons and hydrogens to help us see what's going on here. All right, first step is the chlorine creates a bond to the Lewis acid aluminum, and that generates a Lewis acid complex. And if we were to bond, let me scooch this up real quick. Okay, if we were to now go directly to step 2 with the complex, the molecule that's adding would add at this carbon because that's the one that's bonded to the chlorine. So that could generate that first product that has a 27% yield. But we know that some shift occurs in this reagent to give us that 49% yield. And we can explain that through drawing the carbocation version of this electrophile. So if we then lose the chlorine, we have a carbocation intermediate electrophile here. And this carbocation would then lead to this product. Or we could even say the complex where I highlighted that carbon in blue, that would lead to that product as well. But you might notice that this carbocation is a primary carbocation, which is extremely unstable, but we can make it more stable by doing a hydride shift. And if we do a hydride shift, we've now moved the carbocation to be at that second carbon. And so now we have a secondary carbocation, which is more stable. This carbocation would lead to this product, and because it's a more stable carbocation, that's why we see a higher percent yield for the product where the alkyl group is bonded at the second carbon. Now I do want to note this is not a complete mechanism. I've shown only generating the electrophile. I haven't shown generating the carbocation in the ring or removing the beta hydrogen. So if you were asked for the complete mechanism, this is not enough information. But if you're only asked to explain why these are the observed products, this is a sufficient explanation to say we have these two products because of the two different carbocation intermediates that are possible, or the two carbocation electrophiles that are possible. One is more stable than the other, and that's why we have a higher percent yield for the product that results from the more stable carbocation.